technical reason, which, again, if you work in secure multi-party computation, it's kind of the same reason why commitments are not simulatable. Basically, obfuscated database in this construction, it reveals whether the same value appears in multiple rows, because you can just go through the database and test X on every row. But ideal functionality doesn't, and because of that, the simulator doesn't know which equalities to put into the fake obfuscation. So there is a kind of a somewhat unpleasant fix to this, which is, you redefine ideal functionality so it gives out this information. Given a row index and a candidate value for any field, the ideal functionality answers whether the guess is correct. It doesn't really change anything. It's a technical difficulty. I don't know how to simulate if you don't have this information available to the simulator. And it's kind of the basic commitment problem. You have to give the obfuscated database to the adversary before you know what equalities should be there. And normally it would be solved by some kind of rewinding of the adversary. But here, the rewinding argument doesn't work. Anyway, like I said, this is work in progress, so we're hoping to fix that. It's not terrible. And then there are some practical difficulties. Obfuscation of a single row depends on the entire database, and you can see this because which key bits you learn depends on what else is in the database, so it cannot be incremental, and this seems to be inevitable because this exponential slowdown property makes your access time to a single row of the database dependent on what else in the database, so that's just a feature. And then you need this many bits to obfuscate every access. So squared number of rows times the number of columns. This is not great, right? So you're squaring the size of the database. It's actually perfectly fine as far as theoretical definition is concerned, because the theoretical definition says expansion has to be polynomial in the size of the database. Well, that's polynomial in the size of the database, okay? But still, to obfuscate a database with n rows, you need n squared extra bits. So, maybe not quite practical yet. But as I said, it satisfies this virtual black box property. And, well, let me summarize. So what I hope what have I talked about? So first of all, I'm hoping to convince you that obfuscation is an interesting notion of privacy, that it's somewhat orthogonal to commonly used definitions. So this idea that I make my database indistinguishable from some access function is not quite the same as saying that you cannot get any access to my records. You can ask the question, what are the interesting ideal functionalities? So far we have constructions for lookup and for exponential slowdown. But, there are many access patterns that you might want to obfuscate. And it's not clear. I mean, maybe you can, maybe you can't. We thought that some of them could be unobfuscatable, but every time we tried to get an impossibility result, we couldn't. Which seems to, well, I mean, maybe we're just not seeing something deep in the problem. But the fact that we have been unable to get a single impossibility result seems to suggest that there are a lot of things that can be obfuscated in this fashion. So the good news is that for a large class of access patterns, we have provably secure constructions. The proofs are in the random oracle model, but for some cases, maybe they can be converted into the plain model. But I guess good for the time being. And practical implementation is still a challenge. We just started working on this. We just got the theoretical constructions right. So at some point, we hope to be able to have some practical tools that allow you to do database obfuscation on your own data, But we haven't gotten there yet. Okay, and this is it. Any questions? All right.
Can you go back to that lookup where you explain how you...
I should be able to. This one. Yeah, sure.
These R1s and R2, are they per row or?
This is for each row.
So they are actually R1I or?
Yes, I'm sorry. These are R1I. Otherwise, you would be able, otherwise it wouldn't work. Because otherwise, if this value were the same, then you would be able to compute XOR of Y's where X's are the same without knowing X. Okay?
Right, but that is what you want.
No, that's not what well,
like if you need to know Xi to...
But the problem is that if this random number is no different in every row, but X is, without knowing X, you could cancel them out and compute the XOR of two Y's without knowing corresponding X.
And what about indexing? If you like in these kind of databases, can you use indexes and?
I have not thought about that. I'll give you an honest answer. I don't know what to tell you. Yes.
So in the second version of this, where you had the choosing n missing bits, how do you do insertions? Because it seems that if you want to insert a new row, you have to recalculate the.
Oh yes.
And you don't have the original index value. You don't have the xi value, right? So you have to guess what xi is.
Yeah, you cannot really do insertion because your access time has to depend on what else in the database. So if you insert and you think you're potentially changing access time for every other row in the database. So, like I said, it's not real incremental. It's designed for situations where you take your own database, you obfuscate it, and you just give it to other people, to everybody, and have some notion of privacy. You cannot later add data to that database, at least in the current construction. Yeah.
When you submit a query and the query returns some records with n missing bits, so the next step is you have to guess.
Okay, it doesn't return records with n missing bits. It returns the key to those records with n missing bits. Okay, and if and since this key is used as an input to a hash function, the idea is that you need to guess those bits before you get to the record. So I'm just being very precise here. You get all but n bits of the key. You don't get anything of the record until you get the key. Sorry, I didn't mean to interrupt.
Okay.
So there is no partial leakage of information until you got all bits of the key. Did I answer the question? Oh, okay, sorry. Yeah.
So as a legitimate user, I don't know which guess is correct.
So this is what this field is for, so that you can verify your guess of x. That's exactly what it's for. And I don't know how to obfuscate without it, and that's why I had to hack ideal functionality, so it tells you when your guess is right. Okay.
How is that achieved in the second approach?
In exactly the same way. Like, see, this helps user verify that he found the right row. So for every value that is there, there is a verification. And we're hoping to get a construction where you don't need that. But it's hard. It's hard to get simulation working if you don't have that, because the simulator needs this to simulate. I mean, it's just hard to figure out. Like, no, I'm sorry. What I meant to say is that if you want to do retrieval on this like sort of multi-column database, you need to know that you're in the right row. At some point, you need verification that you're doing it right, because you need to know which bits to guess, okay? So somehow there has to be some indication that tells you which bits you need to be guessing, or at least how many bits you need to be guessing.
How does one know whether he guessed correctly, incorrectly in the key bit? If you need to get two bits?
Yeah, assume that there is some redundancy in this field. Yeah, so he recognizes that. Right. He puts it through the hash function, then he has to decrypt and see, And you can see how this is done in the random oracle model. It's kind of easy. Any more questions?
Sorry. Is this method only applicable to the keys? How about the non-key fields, if they're duplicates and?
I'm not sure I understand the question. What do you mean it's only applicable to keys?
I mean, the keys, they have to be distinguishable from each other, so they're unique primary key fields.
No. I mean, what I call like here, what I call key fields, no, they don't have to be unique. This is just a database. I mean, these are used, like hashes of these values are used to learn the key, but they don't, I mean, I call them keys, but maybe this is misleading. These are not cryptographic keys. This is the actual data in your database, like names and so on. So they don't have to be unique now.
I think what he's saying is this notion of key versus database notion.
They're not database key.
Oh, they're not database keys. Yes, I'm sorry. I'm okay.